All right, thank you very much for the opportunity. Indeed, I will talk about hedgehogs in higher dimensions and application. This is based on joint work with Tanya Firsova, Misha Ljubic, and Raluca Tanase. It's a twofold joint work, and I'll specify what is what when we get to the theorems. So let me just briefly make a tour about hedgehogs in one dimension. So the dynamics of holomorphic germs of C0 with an indifferent fixed point at the origin generated a lot of interest. And I just named a few people only that studied this, the dynamics and linearizability of these germs. So I can name Doadi Haber, Ljubic, Milnor, Perez Marcos, Ishikura-Yokos, and the list goes on, of course. We want to examine just a little bit about hedgehogs in one dimension with the sole purpose of transporting the dynamics properties to two dimensions in an appropriate setting, and that I'll describe in a minute. But first of all, what is a hedgehog? So the theorem of Perez-Marco from early 90s, late 80s actually, you take a holomorphic germ, lambda z plus higher order terms. Lambda is of absolute value 1, and you take a domain, a Jordan domain, around the fixed point, such that the map and its inverse are univalent in the closure of this domain. Then there exists a compact connected invariant set, K, containing the origin, such that this is full, this complement is connected, and it's totally invariant under F. F of K is K, as F inverse of K is K. All right. This is a hedgehog, and this is how it looks like in various cases depending on the arithmetic properties of lambda. So if lambda is a root of unity, then you have the parabolic case, and you have a union of invariant petals, both forward and backward. So in this case, the first case here, lambda is equal to -1. All right. If lambda, for instance, satisfies some Bruno condition or some Diophantine condition, then you have a Ziegel disk, and the hedgehog is compactly contained in the Ziegel disk, in fact. That is the second picture. The third picture, you have the map is linearizable, but you have some extra hair, so the critical point is not in the neighborhood of the Ziegel disk. And the third case is the Kramer situation, in which the germ is not linearizable at the origin. So you have some sort of local structure. We really don't know how it looks like. This is the best image that we have. Michael Jampolsky might know more about this, though, how it looks like. All right. So the tool Perez-Marco used to study the dynamics of germs, the dynamics of univalent germs, is the uniformization theorem. So he uniformizes the complement of the compact invariant set K, the complement of the hedgehog, to the complement of the unit disk, and induces an analytic circle diffeomorphism with the same rotation number on the disk. And then transports results about analytic circle diffeomorphism to results about the dynamics of holomorphic germs in some appropriate set. I do not wish to go too much into details about this construction because, unfortunately, it won't be useful to hedgehogs in two dimensions because of the use of the uniformization theorem. So we'll do some other approach. All right, a bit about the dynamics on the hedgehog. So first of all, one should notice that if the neighborhood U is admissible, meaning the boundary is C1, Jordan domain, then the hedgehog is essentially unique. And it is equal to the connected component containing the origin of the set of points that stay in the neighborhood U under all iterations. So in the parabolic case, as one can guess, this is a union of invariant petals, not very hard to see. Now, suppose that the germ is non-linearizable, and we consider Pn over Qn the convergence of the continuous fraction of alpha. Perez-Marco says that although the germ is non-linearizable at the origin, the dynamics moves under the influence of an irrational rotation. First of all, one should notice that there is a subsequence of iterates f to the power Qn that converge to the identity on the hedgehog. As an immediate corollary, the dynamics on the hedgehog is recurrent on the hedgehog itself. and there are no other periodic points except the fixed point at the origin. So of course, it's hard and sort of exotic to study the dynamics of Kramer polynomials and Kramer germs in general. So this is already saying a lot, although we don't know how it looks like precisely. And a little bit about the dynamics on the exterior of the hedgehog. More or less, if you take a point x from the neighborhood u, but not on the hedgehog, then it cannot converge under iterations to the hedgehog. All right. A little bit about the topology of the hedgehog. Non-linearizable Kramer hedgehogs are not locally connected at any point, so the topology is rather bad, and have empty interior. But they're not really like a bouquet of contour sets or contour lines. They're more complicated than that. All right, one more very interesting theorem about the structure, the local structure of non-linearizable germs is the following. Suppose the following sum, log qn plus 1 over qn is equal to infinity. So this is a refinement of the Bruno condition. The non-linearizable germs have a sequence of periodic orbits which tend to the origin. And the periods q and k verify the Bruno condition here. The result is optimal. This too can be extended to C2 once we learn how the tool to transport results from one-dimensional dynamics to two-dimensional dynamics or even higher dimensional dynamics. All right. So our context is the following. We look at holomorphic germs of C20 for the beginning, and we consider a germ of diffeomorphism of C2 with a fixed point at the origin which is semi-indifferent or semi-neutral. It means that the linear part of the map at the origin has two eigenvalues, lambda and mu, and lambda is of absolute value 1 and mu is of absolute value less than 1. You distinguish three cases: semi-parabolic, when lambda is a root of unity; semi-Siegel, when the map, when you have a holomorphic injection from the unit disk into C2, such that f of semi-conjugates the map to multiplication by lambda, so it's linearizing but in a slice rather. And lambda, of course, is e to the 2 pi alpha. Alpha is irrational in this case. And semi-Kramer, the rest. It's not semi-Siegel, and alpha is irrational. Those are semi-Kramer for us. Such a germ, semi-neutral germ, is in fact partially hyperbolic in a neighborhood of the origin. So partial hyperbolicity means, well, we already saw what it means, but this is, let's go just a little bit to have a closer look of partial hyperbolicity in our context. You have an invariant family of cones, vertical, let's call them vertical and horizontal, and in the vertical you have a strong contraction given by the, dictated by the eigenvalue mu, and in the horizontal direction you have either weak expansion or contraction. So the contraction or the expansion is at weaker rates than the strong contraction. That's what those inequalities over there mean. The crude analysis of the local dynamics of the semi-indifferent fixed point exhibits the existence of a unique analytic strong stable manifold containing points that are converging to the origin asymptotically fast at a rate close to mu, and a generally non-unique center manifold of class Ck for some fixed k, tangent to the eigenspace, the neutral eigenspace, corresponding to the eigenvalue lambda of absolute value 1. And this center manifold, it may not even be C infinity, and in general it is not actually C infinity. So for our purpose, it's enough to assume it's C1. If you want to make it, if you want to increase the regularity, you have to shrink the neighborhood on which you define, or you define your center manifold. So for our purpose, let's assume B is a good enough neighborhood on which the map is partially hyperbolic and the center manifold is C1. So on the center manifold, we have the following three properties. This is general theory, nothing special at this point. You have local invariance of the center manifold. You have weak uniqueness, so if all backward iterates of a point remain in the ball on which you have partial hyperbolity in the center manifold, then the points belong to the center manifold. And you have shadowing. Every orbit that converges to the origin is shadowed by some orbit on the center manifold that converges to the origin. This is a picture of how showing the non-uniqueness of center manifold. So for instance, you could think of this as being a semi-Ziegel situation. You have a strong stable manifold in the center, you have some rotation domain over there, and you have three center manifolds. They're all unique on the set of points that don't escape from the ball, those that rotate, but once you go outside of this ball, they could be anything you want. The first theorem I can cite, what is a hedgehog in 2 dimensions? This is due to joint work with Tanya, Misha Ljubic and Raluca Tanase on, so this shows the existence of the hedgehog. And the tools we use in this theorem, and I'm not going to talk about it now, are purely topological. So, and the tools we developed to prove this theorem in 2 dimensions also apply to prove the existence of one-dimensional hedgehogs by Perez-Marcos. So it's a reproof. It's a new proof of his theorem, but only on the existence part of the hedgehog. So it's a construction that's purely topological without using anything about the uniformization theorem. So if you have a semi-neutral holomorphic germ of diffeomorphism of C2 fixing the origin with eigenvalues lambda and mu, lambda of absolute value 1, then you consider 2 balls, but first of all, I think we could just assume that you consider one ball and such that the map is partially hyperbolic in the neighborhood of the closure of this ball. This replaces the condition from 1 dimension where you took a neighborhood, U, on which the map was univalent, in a neighborhood of the closure of U. Now we want a ball in C2 on which the map is partially hyperbolic in a neighborhood of the ball. All right. Then there exists a hedgehog inside this ball such that it's contained in a center manifold, regardless of the choice of center manifold. So it's contained in all center manifolds that you can define with respect to the ball. It's compact, connected, completely invariant, and full. The complement in the center manifold is connected. So don't forget the center manifold can be defined so that with respect to a neighborhood of the ball, of the closure of the ball. So it's bigger than the hedgehog. 0 is in the hedgehog, so it contains the fixed point, and it intersects the boundary of the ball. This is a crucial property because it has to be big in some sense. It cannot be too tiny. And it comes with a strong local strong stable foliation over the hedgehog. So points converge asymptotically fast at a rate close to the dissipative eigenvalue. So this is what a hedgehog is. This theorem tells us about the existence of hedgehogs. But now we want to understand the dynamics of such hedgehog for germs of C2. Before doing that, this is the picture we should have in mind. It is done by hand, same as Perez-Marcos, but just to see the ambient space, you have a strong stable foliation, a solid stable manifold in red. You have the hedgehog inside the local center manifold. So the center manifolds, it's very interesting. If you have a non-linearizable germ of C2, the center manifolds are not unique, of course, but they're unique on the hedgehog. So there is a structure there, connected, compact, invariant, such that it's contained in all center manifolds that you can define, and the ball over there. So the hedgehog stretches all the way to the boundary of the ball. All right. So what's the tool we have? The tool we have, joined with Misha Ljubic and Raluca Tanase, is the following. To modify the complex structure on the center manifold, which is just C1 for us, such that the map restricted to the center manifold becomes analytic. So the theorem is the following. It's exactly what I just said. The map on the center manifold, there exists a neighborhood W inside the center manifold. The map on the center manifold is quasi-conformally conjugate to a holomorphic map having the same multiplier at the origin as the neutral eigenvalue lambda. And moreover, this quasi-conformal conjugacy is in fact holomorphic on the interior of points that do not escape under backward iterations from the ball. If you are thinking of a semi-parabolic situation, these would be the repelling petals. The petals, the set of points that do not escape the ball under backward iterations. So the quasi-conformal conjugacy would be analytic on the set lambda. But in any case, the rough idea is that you can quasi-conformally conjugate the germ on the center manifold to an analytic map. And now you have the analytic map with the same multiplier that's neutral. This is the one-dimensional part of the talk. You have the machinery developed over there, and you transport the results back to C2. Well, it's in a center manifold, still one-dimensional in this case. All right, so the dynamical consequence, the immediate one, is that there is if Pn over Qn are the approximates of alpha, alpha being the angle of the neutral eigenvalue, then there is a subsequence of iterates, f to the power Qn, that converge to the identity on the hedgehog. And as a consequence, the dynamics on the hedgehog is recurrent, and the hedgehog does not contain any periodic orbits except the fixed point. However, in C2, you have to be careful because, for instance, if there is a strong stable manifold, so of course on the strong stable manifolds, points converge to the origin asymptotically fast. But if you're not on the strong stable manifold, the orbit of Z does not converge to 0, first of all. We can say more about here. But roughly the idea is that the strong stable foliation of the hedgehog is equal to the strong stable set of the hedgehog, to the stable set of the hedgehog as one would regularly define it. The set of points that converge asymptotically fast is the same as the set of points that converge to the hedgehog. A bit more about the linearizability of such transformations. If you have a holomorphic germs of diffeomorphism of C2 with a semi-neutral fixed point, then if 0 belongs to the interior of the hedgehog relative to the center manifold, this is true if and only if the germ f is analytically conjugate to a linear cocycle f tilde, which is lambda x and mu of x times y, and mu is of that form. Mu is the dissipative eigenvalue. So mu of x is mu plus higher order terms. So this is not quite linearizability. In one dimension, Perez-Markov shows that if you are in the interior of the hedgehog, then and you're not, f to the power n is not equal to the identity, then the germ is linearizable. In C2, the situation is slightly more delicate. However, if you discuss about polynomial diffeomorphism of C2, which are global objects, and they have constant Jacobian, then you have a precise condition. 0 is in the interior of the hedgehog with respect to the center manifold, if and only if the germ is linearizable at the origin. Yes? No. Well, you can define a, you have to, what is a semi-Ziegel? It's equivalent to have a Ziegel. With what rotation number? Is it Diophantine or Kramer type? Diophantine or Kramer type? Yes, but it's not the same as in one dimension. You could have, for instance, a germ is, okay. Yes, so you could have a Ziegel, yes, this germ has a Ziegel disk, yes, F tilde has a Ziegel disk, but I'm saying if 0 is in the interior of the hedgehog, if and only if this is analytically conjugate to this. You can rephrase it to what you said, yes, if you want. Okay. Yes. Yes, so the hedgehog will have empty non-empty interior, you said. The hedgehog can have empty interior in the semi-Kramer situation. And it could also have, if you're dealing with parabolic situation, you have a union of petals, it can have interior, but not at 0. 0 is not in the interior. But the hedgehog itself can have interior, yes. Is this what you are asking? Okay. So in the two-dimensional setting, when we talk about polynomial diffeomorphism of C2, we recover the theorem from one dimension, and the situation is much nicer. A little bit more about polynomial diffeomorphism of C2. Henon maps, for instance, are polynomial diffeomorphism of C2. F is non-linearizable in the origin. We assume we're in the situation of a semi-Kramer Henon map or semi-Kramer polynomial automorphism of C2. The hedgehog is inside the Julia set of the Henon map. The intersection of the set of points that, well, let's define it properly. We have J plus is the boundary of K plus, and K plus are the set of points that do not escape under forward iteration. K minus are the set of points that do not escape under backward iteration. J plus and J minus are their topological boundaries. J is at the intersection of the two. J is bounded, and the following theorem says that the hedgehog is a subset of J, and there are no wandering domains converging to the hedgehog. There is a lot to be studied in this situation for the Henon map which is not linearizable or the origin, but this is already some interesting result. A little bit more, we recover, well, we obtain a generalization to Neishull's theorem in 2 dimensions. You have 2 germs with eigenvalues lambda 1, e to the 2 pi theta 1, and lambda 2, e to the 2 pi theta 2, that are topologically conjugate, if and only if theta 1 is equal to theta 2. So this is already of independent interest. It's a generalization of Neishull to a two-dimensional setting. We have actually a generalization of Neishull to a higher dimensional setting. Hopefully I get to the end. All right, a little bit about the sketch of proof. Very brief fast forward. So you take your favorite center manifold, and the most important observation is the following. Some holomorphic structure still exists in the center manifold. You look at lambda, the set of points that do not escape the ball under backward iterations. And the first proposition observation is that the tangent space is in fact a complex line. The tangent space at point x belonging to this set lambda is in fact a invariant complex line. Okay, so this is already interesting. So lambda more or less is analytic, whatever that means, because lambda could be a set of lines. All right, so we need to modify the complex structure on the center manifold. These are the main key points. The standard Hermitian structure on C2 restricts essentially to a Riemannian metric on the center manifold. All right. Every Riemannian metric on this 2 real dimensional center manifold induces an almost complex structure, which we call J prime. All right. J is the standard complex in C2, so this is different than J prime, because the center manifold is just C1. All right. But it's equal to J prime on the set of points x belonging to lambda. Every almost complex structure on a 2-dimensional real manifold is integrable. So there is a parametrization function phi defined from C to the center manifold, such that this diagram, for instance, over there commutes. So W lives in the center manifold, U lives in C, and the map G, the map phi, is a parametrization of the center manifold. It's J prime I holomorphic. In any case, we can restrict the dynamics to a map G induced by this diagram. And now we need to know how far is F from an analytic map. We need to measure how far it is from an analytic map. And it's analytic on some set, and now we just take neighborhoods, Wn, the set of points that stay in W under n backward iterations. So you see the set lambda is already in the nested intersection of all these Wn. So these Wn's are neighborhoods that shrink to lambda. So on lambda, the map is analytic. So now it makes sense. All right, how far is the d bar derivative of F from being 0 on these Wn's? And we will see that it decays of the form O of rho to the n, with rho is being less than 1, some constant. So, all right, so this already transforms into some Beltrami coefficient. But first of all, let's define the object. So Wn is what I just said. UNs are the corresponding sets down below on the diagram. X is the corresponding set of lambda. This is the set of points that do not escape from the neighborhood U under all backward iterates of the map G downstairs. All right, a first estimate on the d bar j prime derivative of f. I put there a formula, but I don't really expect you to follow this particular computation. The important thing is that this derivative of f on the set Wn of points that do not escape under the first n backward iterates is bounded by rho to the n, where rho is some constant less than 1 given by the invariance of cone fields and the properties of cone fields. This translates to saying that the d bar derivative of g, the g is already in the complex plane, a map in the complex plane. D bar derivative of g is 0 on the set of points that never escape the ball, or the domain U. And the d bar derivative of g on the set Un is bounded by some constant times rho to the power n, for rho less than 1. Okay, this is a little bit about the Beltrami coefficient and the complex delimitation, but I have a feeling everybody knows about this, so I will move on. So you take sigma naught, the standard complex structure on the complex plane, the standard almost complex structure on the complex plane. You look at sigma n, the Beltrami differentials, which are the pullbacks under G iterated minus n times of sigma 0. These are Beltrami differentials defined naturally on the sets Un. Based on the previous estimates, we immediately see that the essential supremum of sigma n is bounded by k, which is bounded away from 1. So it's k less than 1, and they're bounded uniformly of n, independent of n. And this allows us, using the measurable Riemann mapping theorem, to say already that the map G, or G inverse, defined on these domains U intersected G of U with values U intersect G inverse of U, is quasi-conformally to an analytic map H. More or less, roughly, the idea is that using this lemma and the fact that the Beltrami differential sigma n are bounded away from 1, it's enough to ensure that the map G on the set U is quasi-conformally conjugate to an analytic map. So the domains in this theorem are just to make it well defined, but that's the essential part. All right, to see now that the map H has the same multiplier as the neutral eigenvalue, we could do two things. First, we could use a generalization of Naishull's theorem due to Gamba-Odole Calves-Pecou, and this tells us immediately that lambda has to be H prime of 0. H prime of 0 is this analytic map over here, has to be equal to lambda. Lambda is our neutral eigenvalue. Or we could use the Hedgehog construction from the theorem that I first introduced in 2 dimensions. Because if you have a hedgehog, you will not be able to induce on a circle, you'll not be able to associate to our topological hedgehog. You'll not be able to associate an analytic circle diffeomorphism as Perez-Markov, but you can associate a homeomorphism of the circle with the same rotation number. And using this and the same machinery as in 1 dimension, you could prove that, in fact, the hedgehog for the map H must have the same rotation and the same multiplier at the origin as the hedgehog for our germ. Hence, H prime of 0 is equal to lambda. So, one more theorem. Everything that I talked about extends to germs of Cn0 with precisely one neutral eigenvalue. So you have n eigenvalues of the linear map at the origin. Some of them are inside the unit circle. Some of them are outside of the unit circle, on the unit disk. And precisely one is on the unit disk, on the unit circle. In that case, the map on the center manifold, but this is now, you need to define it. It's the intersection of the center stable and the central unstable. But in any case, the center manifold is one complex dimension. It's 2 real dimensions, so it's 2 dimensions. So all the machinery that I discussed goes through, and the map restricted to the center manifold is quasi-conformally conjugate to an analytic germ of the form lambda jz plus a higher order term, lambda j being the neutral eigenvalue. So this allows us to transport the results from 1D to even higher dimensional setting. And I think this is it.